Well, good morning, everyone. So, I hope everyone are doing well. So, today we will start our discussion about the nonlinear data structures, and we will we'll start our discussion about the trees, and I will introduce you the one type of tree that is a binary tree today. Okay, so in the previous classes, we have discussed about the various kinds of data structures we generally have. We have just differentiated between the data structures, two type of data structures we generally have. One is a linear data structure and non-linear data structure. So now, if we talk about more about this, uh, type of data structures we have the other type of data structures which is non-linear. So earlier we discussed about the linear and non-linear data structures, but now we will talk about the non-linear data structures which we have. Okay, the non-linear data structures in the data structure in data item is connected to several other items here. So it is not just connected to one data item, it is connected to several other data items. And the data items in this nonlinear data structure represent hierarchical relationship. They have the hierarchical relationship which is shown in case of nonlinear data structure, and each data item is called as node. Every data item is called as node here, and we have two different types of nonlinear data structures: trees and graphs. So a tree is a data structure consisting of nodes organized in a hierarchy here. So one after the one below the another, the the nodes are been organized in an hierarchical way. So this tree data structure, which stores the information naturally in the form of hierarchical style. So it is the data structure compared to arrays, linked lists, queues, and graphs. So it is a nonlinear data structure compared to the arrays, linked list, stack, and queue. Okay, so we have the different terminology which we need to use. Also, we will go to this and we will discuss one by one. So a tree is a non-linear data structure which organizes data in a hierarchical structure in which and this is a recursive definition. Recursive definition in the sense anything which is below it will again become a tree. Like for example, see here. So this entire thing is a tree, and again anything which is below it is again becomes a tree. Means A, under A we have B and C, and again under B we have D, E, F nodes. So now it becomes another tree there. So likewise, CG again becomes another subtree here. Okay, like we have EF, though it may be of two nodes, again they become a subtree here. So it is an data structure where the things have been organized in a hierarchical structure, and this is a recursive definition. Another definition we can see here say that a tree is a connected graph without any circuits. So it is a connected graph without any circuit. The meaning of that is a graph is nothing but where we have the nodes and edges which are connected to one another. But the possibility of anything in case of uh, graph is we may have a circuit. We may have a circuit means uh, we can have a cycle in case of a graph. But whereas in case of a tree, we don't find any circuit there. We don't find any circle. And if in the graph there is only one and only one path between every phase of vertices, then the graph is called as a tree. So another definition we can say that that in a graph, if there is only one and only one path between every pair of vertices, then it is called as a tree. Means you can't have multiple paths. Means from C, for example, to go to F here, we can traverse from A to C and F. That is the only path which is existing. So we cannot go reach F in some other way. So the only path we have is F. So even for example, uh, uh, even for example, I want to go from D to G, then I have to go from D to B, then B to A, then to C, then to G. So that is the only path which is existing. I can't find another path. Whereas in case of graph, see here, to reach from one node to another, for example, from if I want to go to V4, from V1 to V4, then I can go traverse through V3 and V4, and I can also go from V2 to V4. So if it is an undirected graph, of course, in a directed graph, you can come across with some problems where you may not find a path from one node to another. Okay, so that is what actually is about the definition. Next, we have see, and another example is given. In case of this particular tree here, we have there is a connection between D and E. Now we have a cycle here. We have a circuit here. So this is not actually the graph. Sorry, this is not actually the tree. In fact, it is a graph. Whereas in case of this particular thing, so we have a tree. We have a tree. Okay. I mean, it is called as a tree because we are having only one path. From one node to another node, we are just having only one path. Now we can term it as a tree. Next, the properties of a tree, that there is only one and only one path between every pair of vertices in tree. So the properties of tree are there is only one and only one path between each pair of vertices in a tree. The next is a tree with n vertices has exactly n minus 1 edges. A tree with n vertices will have exactly n minus 1. Means what is an edge here? A connection between two nodes is actually called as an edge. So here this A, B, C, D, E are actually nodes, and a connection between any two pairs of nodes is called as an edge. Okay, so there is if there are some n nodes here, we can have n minus 1 edges. So for example, see here we have five nodes here. Then we have only n minus 4 edges from A to B1, A to C2, C to D3, and C to E4. Okay, then a graph is a tree if and only if it is minimally connected. So you can call graph as a tree if it is only minimally connected. Minimally connected means there is only one connection, there is only one link between each pair of nodes. And any connected graph with n vertices and n minus 1 edges is a tree. So any connected graph which is actually having n minus 1 edges, okay, sorry, n vertices and n minus 1 edges is called as a tree. Then different terminology, you need to have idea about this terminology, the entire, we need to know what is the parent, what is the chair, sublinks, degree, internal node, deep node, level, height, depth, subtree, forest, root, edge, all this terminology we need to we should have an idea about this. And also you must be thorough with this terminology because these may be asked in interviews also. So once you post that you are aware of data structures. So if the interviewer chooses the tree, that nonlinear data structures, they may ask you about this definition. So just be ready with those definitions. Next, the first definition which we will look for is about the root. What is the root here? The first node from where the tree originates is called as a tree. It's a root node. Means from where the tree starts is generally called as a root node, and in any tree there must be only one root node, and we can never have multiple root nodes in a tree data structure. So see the property. So there means now in this particular tree A is a root node. So that is the only root node we have. That is the only root node we have from where the entire tree has been started. Okay, then there should be only one root node, and you cannot have multiple root nodes. Of course, now this is an entire tree. I can make this particular portion as a subtree. I can make this particular portion as a subtree, means from this B, D, E, F, I, J. Now this is a subtree in which B is the root node for that subtree. Likewise, CG HK for C is the root node for this subtree. Now if I take EIJ, so it is again a subtree where E is the root node for that small subtree there. Of course, those are all been connected, so we can say that we are having only one root node here. So A is the only root node. Then edge, as I just said, that anything which is connecting between the two nodes is called as an edge there. And if they are having n nodes, then there will be exactly n minus 1 edges. So if there are n nodes, then we will have n minus 1 edges. Okay. Next we have the parent. So the node which has the branch from it to any other node is called as a parent. Means from where actually the other node branches are called as a parent node. So in other words, the node which has one or more children is called as a parent node. So the node which has one or more children is called as a parent node, and in a tree, a parent node can have any number of child nodes. So this is the feature of of the parent, that it can have any number of children. So it is not restricted to two or three or one. It may have any number of children there. Of course, we will discuss about some other types of trees later on, where we are restricted to have only one or two childs or no childs. Okay, so such are the binary trees, which we will discuss later on. But in general, a node can have any number of childs. Okay, for it. So for example, now say A is a parent of B and C, and now I can say the B is the parent of D, E, F, and E is the parent of I, J. Likewise, C is the parent of G and H, and G is the parent of K. Okay. As I just said, these are all things. So next we have the chain. The node which is a descendant from some other node is called as a chain node. Means the one which has been descendant here. So for example, I and J are descendant from E. So those I and J are called chain nodes of E. Likewise, D, E, F are the descendants from B. So D, E, F are called the chain nodes of B. Likewise, we have K, which is the descendant from G. So K is called the child of G. So G is the parent of K, and K is the child of G. G and H are the childs of C. C is the parent of G and C. Likewise, B and C are the childs of A, and A is the parent of B and C. Okay, and all the nodes except the root node are child nodes. So all the nodes which are except the root node, means for A, all remaining are the child nodes only. So I had just spoken about the subtrees here, but we can say that apart from A, all are called as child nodes. Okay. Next, have the sublinks. Sublinks in the sense, the nodes which belongs to the same parent are called as sublinks. So in other words, nodes with the same parent are called as means the one which are having the same parent are called as sublinks. Like B and C are the sublinks here because the parent of B and C is A. Okay, then we have D, E, F are the sublinks because D, E, F are the means the parent of D, E, F is a B. Likewise, we have G and H, which are whose parent is C, and because of that, G and C, H are called the sublinks. And likewise, we have I and J, which are also the sublinks because their parent is E. Next, we have the degree. What is the degree of a node? The degree of the node is the total number of children of that node. Means the number of children a particular node has. And the degree of a tree is the highest degree of the node among all the nodes in the tree. So remember that the degree of the tree will be the highest degree of the node among all the nodes in the tree. Means, for example, see here, total number of children of the node. So A, the degree of A is 2 because it has only 2 children. Then we have the degree of B is 3. Okay, because it has 3 children. The degree of E is 2. And the degree of C is 2. And if I say what is the degree of G, it is only 1. And what is the degree of H, it is 0. But overall, if someone asks you what is the degree of a tree, Then what is the highest value here? The highest value is 3. So we can say the degree of the entire tree is 3, because at most we are having, means the largest we are having is 3 children. That's what it is saying, that the degree of the tree is the highest degree of the node among all the nodes here. Okay. Next we have the internal node. The internal node, the node which has at least one children is called as an internal node. And internal nodes are also called as non-terminal nodes. The one which is having at least one children is called as an internal node. And every non-leaf node is an internal. Means the non-leaf. We will discuss what is leaf node later on. The leaf node is the last one which is having no children. So internal node is the one which is having at least one children. Now, C is the B is an internal node, C is an internal node. Likewise, G is an internal node, E is an internal node, because at least they are having some children there. But we cannot call D, F, and H as internal node. Likewise, you cannot say I, J, K as internal nodes here. Okay. The leaf node, as I just told you, that the node which does not have any children, the one which doesn't have any children, is called as a leaf node. Leaf nodes are also called as an external nodes or the terminal nodes. Okay, so means the one which is having no children is called as a leaf node. So H is a leaf node, I is a leaf node, J is a leaf node, K is a leaf node. We can say D and F are also the leaf nodes. Okay, next we have the level. What is the level here? In a tree, each step from top to bottom is called as a level of the tree. In a tree, each step from top to bottom is called as a level of a tree. The level count starts with 0 and increments 1 at each level. Okay, the level of the tree is the count. Okay, the each step from top to bottom is called as a level of a tree. So we can say that A is at level 0, B and C are at level 1, D, E, F, G, H are at level 2, and I, J, K are at level 3. So this is what actually is the level of the tree. Okay, now the next terminology, next term which we need to be aware is about the height of the tree. What is the height of the tree? Is the total number of edges that lies on the longest path from any leaf node to the particular node is called the height of the tree. The total number of edges that lies on the longest path from the leaf node to the particular node is the longest path from the leaf node to the particular means. So if you take a particular node, so what is the height of the B? What is the height of the B? Means the longest path. See here, from D to B we are having only one edge, but in fact the longest path will be from I to E to B there. So we are having two edges here. Then we can say the height of B is 2. The height of B is 2. And the height of H is 0 because it doesn't having any leaf nodes here. And what will be the height of A here? The height of A will be 3. 1, 2, 3. 3 edges here. Okay, so the last means we can simply identify that the last level, whatever will be the last level, that will be the height of the tree there. Means starting from 0, what will be the bottommost level, what will be there, that will become the height of the entire tree. Okay, so the height of the node means, so you can identify here the height of the node A is 3, height of the node B is 2, height of the node C is also 2, for D it is 0, E 1, okay, F 0, G 1, okay, H 0, and I, J, K 0. Okay. Then the depth, the total number of edges from the root node to the particular node. Now you are coming in the reverse order. Starting from the root node, starting with the basic root node, whatever the select. So the total number of edges from the root node to the particular node. So you can choose a particular node, then you can say that it is the depth of the tree. And the depth of the tree is the total number of edges from the root node to the leaf node in the longest path. Means overall, what is the depth of the tree? Here, the total number of edges from the root node to the leaf node is the longest path. So always the depth of the root node will be 0. The depth of the root node is 0. The terms level and depth can be used interchangeably. So you can use the level as well as the depth interchangeably. So you can say that the depth of B is 1, means starting from the root node, the depth of B is 1. From starting from the root node, the depth of the H is 2. Okay, likewise, the depth of the C is also 1. The depth of the D, E, F, G, H can be 2. Okay, and for I, J, and K, it will be 3. Okay, then you have the subtree. So already we have seen about this subtree. In the tree, if each child from a node forms a subtree recursively. In a subtree, each child forms a subtree recursively. Every child node forms a subtree on its parent node. Every child node forms a subtree to its parent node. So we have A, the entire tree which is given. Then we have the B, D, E, F, I, J, which forms a subtree. Then we have the C, G, H, K, which forms another subtree. Then again we have G and K, which is also forming a subtree, which is not mentioned here. Then we have the E, I, J, which is also forming a subtree. Then you have a forest. A forest is a set of disjoint trees. Forest, we can call it as a set of disjoint trees, means the trees which are being not being joined here. So this is an forest here. So we have two trees differently, but two different trees which are mentioned here, but we can call them as a forest here. Okay. Next, after this, let us discuss about the various other type of subtrees. Means mostly we will be dealing with the binary trees here. We have the binary trees which we will be dealing. So next I would like to discuss about the binary trees. What is a binary tree, how it is constructed, what are its features. So a binary tree actually is a tree which are having two nodes, at most two children there. So previously I said that a tree can have more than one children, means it can have more than 2 or 3 children here. But whereas in case of binary tree, the first basic rule which we are supposed to follow is a binary tree is the one which is a special tree data structure in which each node can have at most 2 children. Only 2 children are allowed in this. Okay, and each node has either 0 child or 1 child or 2 child. So as I just told you that normal tree can have more than 1 children, means one children or more than one children or no children. But in case of the binary tree, it is restricted to only 2 children there. You can have either 0 childs or 1 child or 2 childs. Now here an example is given. So in this tree, see node with only 1 child, node with 0 child, and a node with 2 children. So B is having 2 children, A is also having 2 children. Then we have D, which is having 1 child, and G, E, F, which are having no childs at all. Okay, so this is what actually is a binary tree. Okay, next we have unlabeled. So unlabeled binary tree. What is an unlabeled binary tree? So if the nodes are not assigned any label, it is called as an unlabeled binary tree. So no nodes are assigned here, see, so it is empty, then it is called as an unlabeled binary tree. Okay, so the number of different binary trees possible with n unlabeled nodes. So this is a formula which is given here. The number of unlabeled means the binary trees which you can form using this unlabeled nodes is 2n-cn. Okay, 2n-cn by n plus 1. Formula here is 2n-cn by n plus 1. For example, here see if they are having 3 unlabeled nodes, then we have 6c3 by 4. 6c3 by 4 is 5. Okay, 6c3 by 4 is 5. So permutation means the combinations which you can form here is 5 combinations here. Using 3 nodes, we are having 3 nodes, you can find the 5 combinations. So what are those 5 combinations here? See, these are the 5 combinations. You can have such trees here using these 3 unlabeled nodes. Using these 3 unlabeled nodes, we are having 5 combinations here. Okay. Next, I have the labeled binary tree. A binary tree is labeled if all the nodes have been assigned with a label. Now, if you are having a label here, then it is called as a labeled binary tree. So here A, B, C have been labeled. Okay, so it is called as a labeled binary tree. So the number of different binary trees possible for n labeled nodes. The formula here is 2ncn by n plus 1 into n factorial, means into n factorial. In the sense, these are actually 5 into 3 factorial. Means if suppose you are taking n as 3 here, so 2ncn by n plus 1 will give you the 5 here, and 3 factorial, 6 threes, sorry, 3 factorial is 6. So 6 into 5. So 30 different combinations can be formed here. So, with 3 labeled nodes, using that formula, we can have around 30 different possible binary trees which can be formed using these labels. Thus, with 3 labeled nodes, 30 labeled binary trees can be formed. Each unlabeled structure gives rise to 3 factorial, that is 6 different labeled structure. Okay, for example, see here, if this is taken, then we have A, B, C, then we have B, A, C, then C, A, B, then A, C, B, B, C, A, and C, A, B. These are all the combinations where the position of the nodes we are changing. We're changing the position of the labels here, and we are defining. Likewise, if you go for uh, likewise, if you go for another structure, like if you go for this first type of structure, like you can say A, B, C, then you have B, A, C, then you have B, C, B, A. Like that, you can form again 6 different structures. So 6, 6, 6, 6, 6. So 30 different structures will be formed. Okay, then we have the different kinds of binary trees with us. So binary trees can be of rooted binary tree, full binary tree. Then you have skewed binary tree, almost binary tree, and complete perfect binary tree. So from here onwards, I would like to discuss about these things in the coming class. Okay, so just get thorough with these definitions. Uh, we'll continue in the next class. So, is there any doubt regarding to this class?
No, sir.
Okay. So, have you practiced the programs which I have shared with you? Then we have a roaring silence, no answer from your side.